All right, just notice that when I ended that last video of part one, that I didn't talk about the graph. So again, here on your graph, if you want to go open circle above the -3, open circle 3, shade in between, that can be our graph. All right, example 3, working the second part now. Now let's look at an example where we have something other than 0 for our a. So let's say we have x minus 2. So we're centered at 2. We're going to run the test the same way. Just be careful in how you write out your binomials raised to power. Don't lose anything or misplace anything. So our first fraction is the a sub n plus 1. So where you see the n's, we'll put an n plus 1. Remember, we're dividing by a sub n or multiplying by its reciprocal. So it's right here. Flip it. And we'll do our simplifying again. So this 5 to the n plus 1, we can rewrite that again as we've done in the past. 5 to the n times 5. X minus 2 to the n times x minus 2 to the first. You're more than welcome to put the ones as a power as a reminder. Cancel the 5 to the n's, cancel the x minus 2 to the n's, and we're left with x minus 2 over 5. And again, there's no n here in our expression. So this is our limit. We keep the absolute value bars again because we don't know if x is positive or negative. We're going to set this less than 1 and find where our interval of convergence is going to be. We'll solve this for x, if you will. So we drop the absolute value bars. We'll put -1 less than on the left side of our variable expression. We'll put less than 1 on the other side. Got to get rid of the division of 5, so we multiply 5 to both sides. Just as a note, now that you have your x minus 2, that's your center about a, left in your compound inequality, this 5 is your capital R. That's your radius. Add the 2 to the outsides. That gives you -3 is less than x is less than 7. This is our proposed interval of convergence so far. But again, we have to test the endpoints. So part 2, let's go test the endpoints. We'll plug in the -3. That's going to give me -3 minus 2 is going to be -5 to the n over 5 to the n. And this is kind of like what's happening in our last problem. We get -5 over 5, which is -1 to the n, which we saw that that's a geometric series, and that's going to diverge. Your r is going to be 1. And if we put in a 7, I'm thinking we might get the same thing here. 7 minus 2 is going to be 5 to the n over 5 to the n. That's 1 to the n. And therefore, your r is still a 1. It still diverges. So everything stays the same. The interval of convergence and doesn't change with its endpoints, and our radius of convergence is equal to 5. Now again, divergence does happen more times than not, but you still have to double check. Every once in a while, one sneaks in there and it does converge. All right, so let's get started with this example. Now we have a factorial in the problem. All right, our a is going to be 5. We are centered around 5. So using your ratio test, we're going to have x minus 5 to the n plus 1 over n plus 1 factorial times the reciprocal of this fraction, n factorial over x minus 5 raised to the n. Again, we'll do our cancellations here with our exponentials. X minus 5 to the n power times x minus 5 to the first power. And our factorial rule, this will be n plus 1 times n factorial, so we can cancel the n factorials. So now this simplifies, and now here's a case, whoa, n stayed in our limit. And since n is in the denominator, as n approaches infinity, this denominator is going to constantly keep getting bigger and bigger and bigger. This up here is technically going to be a constant for us. So this is approaching 0. So since the limit's equal to 0, that's one of your 3 cases. For all x and 0 is less than 1, the series converges for all possible x values in the ratio test. So here's the case where your radius of convergence is infinity, and our interval of convergence is -infinity to +infinity. Now, notice we don't have to go check our endpoints because we can't physically touch negative infinity or positive infinity. So we're done. Example 5. Let's do another problem here. We have x minus 4 to the nth power. Now it's times n factorial. So again, applying our ratio test, a is 4. We're centered about 4. We have x minus 4 to the n plus 1 power times n plus 1 factorial. Now divided by, now I didn't multiply by the reciprocal here because there was no fraction to work with, so I'm moving all of this into the denominator. X minus 4 to the n power times n factorial. Start simplifying again. X minus 4 to the n power times x minus 4 to the first. Cancel the x minus 4 to the n power. N plus 1 times n factorial. Cancel the n factorials. We are now left with x minus 4 from this extra one here and the extra n plus 1. And again, n is in our limit as n goes to infinity. It's x minus 4 times infinity, so we are going to infinity. Since the limit is infinity for all x except the center, x equals 4, then that means your radius is 0 and our interval of convergence is only the value of 4. So here I put braces. It's a set. I'm listing just that one particular value, or you can leave it as x equals 4. But your radius of convergence is definitely 0. When this happens, again, we're done. You don't have any endpoints to test because there's nowhere to go for endpoints. Your radius is 0. All right, given example 6. Ooh, looks like we got a negative 1 raised to a power. We might be working with an alternating series here somewhere. All right, so let's find our interval of convergence. We have x minus 5 to the n plus 1. So your a is 5, so you're centered around 5 again. In the denominator, you have n times 5 to the n power. So we're going to go to our ratio test. Lots of n's to keep track of here. So negative 1 to the n plus 2 plus 1 will be plus 3. X minus 5 to the n plus 1 will make that plus 2. My n being multiplied to the 5n becomes the binomial n plus 1, and the 5 is raised to the n plus 1. Well, since this is a fraction, I'll flip it to its reciprocal so we can do some canceling here. All right, so lots of things to look at here. Here, my x minus 5 to the n plus 2 will become n plus 1 times an extra binomial x minus 5. The 5 to the n plus 1, I'm going to change that to 5 to the n times 5. So that cancels out the 5 to the n, leaves the 5 down here. Let's see, what else do we have? We already canceled this. Oh, and then we got our negatives here. Now the negatives, seeing that we're inside of absolute value bars, we really don't care what happens to these negative ones because they're going to become absolute value and made them positive ones anyhow. So we just cancel them both out. That's because of the absolute value bars. And so we have our n from here and your n plus 1 back over here. All right, now, whoops, we have 2 n's left over in our limit. Well, if we look at this, again, treat the x minus 5 over 5. Think of those as your leading coefficients on this n. This is n to the first, this is n to the first. So technically, this part of the fraction here, that's going to approach 1. So x minus 5 over 5 times 1 is just going to be x minus 5 over 5. Still in our absolute value bars because we don't know if x is positive or negative. So we'll set that absolute value less than 1, turn it into a compound inequality, multiply to get rid of the division of 5, and now you found your center, x minus a, so your radius here is 5. Add the 5 to both sides, so 0 is less than x is less than 10. This is my proposed interval of convergence. Now we test the endpoints, the 0. So I put 0 in for x. That's going to leave me a negative 5 to the n plus 1 over n times 5 to the n. So what I'm going to do here is, since I already have a negative 1 to the n plus 2, I'm going to factor out this negative 1 off my 5 so I can compare my 5 with my 5 down here. So that's going to make this negative 1 to the n plus 1 power. Now, these two can be multiplied together. They're like bases. So therefore, I add the exponents together, and that gives me negative 1 to the 2n plus 3, n plus n and 2 plus 1. And of course, my 5 to the n plus 1, now that these bases are exactly the same, I'll break that down. So I can cancel my 5 to the n with 5 to the n. And over here, you got to take a really close look at what's happening in your power. My n starts at 1. It's going to be an odd and an even, an odd and an even, 1, 2, 3, 4. But when I multiply it by 2, that's going to make that product always an even number. And if I add a 3 to it, an even plus an odd is always odd. So my power is always going to be an odd. That means it's going to stay negative 1 for every single term. So that's like saying, okay, take this negative 1 to an odd power, just multiply to that 5 and make it negative 5 over n. Everyone agree with that? Thumbs up. All right. Thumbs up. Here we go. So now we have negative 5 over n. And as I test this, this is a p series. All right. N to the first power. So this is going to diverge. P is equal to 1. When 1's greater than or equal to 1, our p series diverge. Okay, let's test the 10. Now I put the 10 in for my x, so 10 minus 5, that's going to give me a positive 5. So now I don't have to factor out the negative 1 like we did up here. We can just start to work on this part. So now that gives me 5 to the n times 5, and we can cancel that. And so now my negative 1 stays. It's going to be an alternating sign. So here, we're going to have to use your alternating series test. All right, up here, it was negative 5 all the time in the numerator. Now, it's going to alternate back and forth. When n is 1, that's 3. They'll start out as negative 5. When n is 2, that's 4. That becomes a positive 1, so I'm alternating back and forth. So the alternating series test says get rid of the negative 1, just focus on the 5 over n, take its limit. If it's equal to 0, we continue. Well, yes, when n goes to infinity, your bottom's getting bigger. We are going to approach 0. All right, then step 2, show that a sub n plus 1 is less than or equal to a sub n. So 5 over n plus 1 is less than or equal to 5 over n. Cross multiply, sure enough, yep, we're always 5 bigger here on the right, so both are true. This endpoint converges. So therefore, my interval of convergence is 0 with left parentheses, comma 10, now with a bracket. And that ends the second part of 11.8.